All right, so this example, we have two wheels fixed to rotate about a frictionless axis that can rotate free relative to each other. They have a common center, and they're perpendicular to the page. And there are four forces that are exerted tangentially, which is good because if we remember torque, RF sine theta. If they're tangent or exerted perpendicular, then the sine of 90 degrees is 1. So for this problem, we're just going to worry about torque equals R times F. But if they're exerted at an angle, obviously that would change. And we want to know the net torque. We've done a lot with the sum of forces all year. But for net torque, we're going to be looking at the sum of the torques equals, I don't know. What may be helpful is to think about the four different forces, and maybe I want to label them because we'll just go around in order. We have four of these. So if I think about force 1, and remember, that's before we jump right into that, counterclockwise torques are positive and clockwise torques are negative. So if I jump right in, force 1 is on the outer axis, and that means we have a distance of 3r times F. Go to the next one. Now that is clockwise, so I'm going to have a force of 2F, and that's also on the outer R, so that's 3R, or I switched my order here. Now force 3 is counterclockwise, so we're going to add it, and that's a force of F at a distance of 2R times F. And then the orange one is also in the counterclockwise direction. So we're going to add it, and that's a force of F at a distance 3R. So now we're just going to multiply out and see what we get. So 3RF minus 6RF plus 2RF plus 3RF. So the 3 combines with the 2, 5 plus 3 is 8 minus 6. We should get 2RF, or choice B. Okay, so one of the next topics that was suggested was circular motion. Here we have a 1,200 kilogram car flying, really driving, around a 45-meter unbanked corner, where 45 meters is going to be the radius. So if the driver takes this thing in anything more than 20 meters per second, they will spin out and crash. So that's going to be our maximum friction. If we know if it's unbanked, friction has to be acting as the centripetal force. So anytime that I have friction involved, I probably want to know what the normal force is, because friction, as you remember, is equal to mu Fn. And remember, there isn't a centripetal force, but friction will act as the centripetal force. So that's providing the acceleration towards the center, which is allowing this car to turn around the corner or curve. So first thing that I want to do is, it's helpful to draw a picture, and I'm not very good at 3D pictures, but if we have a 45-meter radius, here's our car, and it's going at 20 meters per second. Let's kind of have a side view, draw a free body diagram. So in this case, friction is the centripetal force, going to point towards the center. We have the normal force upwards and the force of gravity which is downward. So remember, when we do have an acceleration around a curve, so we only care, or we used R a lot, the only towards the radius. So the only force that's towards the center of the circle is this force of friction. And remember, centripetal acceleration equals v squared over r. So I'm going to plug that in. So I have force of friction equals mv squared over r. Now we are given the mass of the car, and therefore it's on a horizontal surface. That means that using 10 meters per second squared, the force of gravity on this car is 12,000 newtons. The normal force is therefore also 12,000 newtons. So if we plug in, we get mu times Fn equals mv squared over r. And now we are ready to plug in some values. So we're looking for this coefficient. Here's a little mistake here. It should say kinetic friction, since this car is moving. Given the mass is 1200. And when I multiply that out, I should get a coefficient of kinetic friction of 0.89. So these are definitely good tires with a lot of grip. Now we know that the only thing that influences the coefficient of friction is the two materials that are in contact with each other. Therefore, for part B, that's going to stay the same. So now we have force of friction equals mv squared over r, where we know and we actually don't need to plug in for this case, so I can actually take a step back because all we're looking for is the friction. And we know the mass is 1200. Try to squeeze it in here. It's now moving at 15 meters per second. That's squared all over. The radius has not changed, so 45 meters. Sorry, it's pretty sloppy over here. We multiply it out, we should get a force of friction of 6,000 newtons. Okay, so here what we have is a momentum problem. There's going to be some energy in here. We have springs, so we have Hooke's law. Definitely can have some simple harmonic motion, so I thought this would be a good problem to include to kind of look at everything. So we have block of mass m resting on a horizontal frictionless table, and it's connected to a relaxed spring. Now, a second block of mass 2m and initial speed v0 collides and sticks together. Therefore, we have an inelastic collision. So what I want to know is the speed v after the blocks collide. So I'll try to do my best to keep it neat here. We have momentum before equals momentum after. Now, remember, this formula works for every single momentum problem. Let me do it up here. We have the mass of 1 times the v0 1 plus mass 2 times v0 2 equals mass 1 v final 1 plus mass 2 v final 2. In this case, since they both stick together, it is going to have the same final velocity. So let me go ahead and set up this formula. Let me just get it going. So we have the mass of 1. Now this block is just sitting there, so that's going to be all the momentum before the collision, equals, they both have the same final velocity, times m1 plus m2. So now let me plug in specific values. We have 2m traveling at a speed of v naught equals the velocity we're looking for times the mass of 1, which is 2m, plus the mass of the block sitting here, which is just m. So we get v times 3m equals 2m v naught. We can divide both sides by 3m. And we should get 2/3 m times v naught. And there we have it. Actually, we could cancel these m's. So the answer would most likely look 2/3 times v naught. The m's definitely cancel. Okay, now we're on to part B. Okay, so in part B, we are looking for x, which is the maximum distance that the spring is compressed. And anytime we're talking about springs in the back of our head, we want to know the potential energy stored in the spring is 1/2 kx squared, and Hooke's law Fs equals kx. Always helpful to have those handy in case we need them. Not sure necessarily we are. And in order to figure this out, we're going to have energy initial equals energy final. Remember, life begins with Li, which doesn't apply here, but it's still worth saying. Now, initially, or let's think about it finally first. When this is compressed and comes to a stop, it's going to be all potential energy. Since it stopped moving, it has no kinetic energy, and it is all potential. Now, when this block is first moving, it has all kinetic. But at the moment it collides, it also has all kinetic. Now, we can't use the kinetic energy that it has at this point because in an inelastic collision, kinetic energy is not conserved. Therefore, we have to use the kinetic energy right when it first collides, so at this point. So initially we have kinetic, and that's converted into potential. If we plug in for these two formulas, 1/2 mv squared equals, that's an equal sign, sorry it's messy, 1/2 kx squared. We can get rid of these 1/2s, and we have mv squared equals kx squared. And what we're doing is we're looking for this x. And it might be helpful to solve for x squared before I even plug in any values. So if we get x squared by itself, we have mv squared over k equals x squared, and we want to get rid of that, so we gotta take the square root. But remember, I gotta plug in, and what I have for the velocity is this 2/3 v naught, and when the masses are combined, it has a mass of 3m, so I can plug in. We have 3m for the mass, 2/3 v naught, which is squared, all over k. Let me grab a calculator. I can clean this up a little bit. So in my calculator, I did 2/3. I squared that and got 0.44. I multiplied that by 3. I get 1.33. Did math fraction, and we get 4/3. So when we clean this up, we get x equals the square root of 4/3 v naught squared over k. And this would be my final answer.